All right, folks, it's Bass Action, back in action here. In this video, we're going to do some applications of the odd and even and periodic properties. We're also going to look into Pythagorean identities and some complementary cofunctions, all of which we're going to use in the remaining sections of this chapter and the next chapter. So let's jump into our odd and even properties. First, let's just recall our information from last semester that if a function is even, then f of negative x is going to equal f of x. And if a function is odd, then f of negative x is going to equal negative f of x. As you're analyzing these problems here, we want to simplify these and clean these problems up. What we basically want to do is just identify what's even and what's odd, and the easiest way to do that is just to simply recognize that the only even functions that we have are cosine and secant. So these are going to be our even functions. Now, if a function is even, and we know that f of negative x is equal to f of x, then when we see these negative inside a trig function, we can simply drop them. So we can go from the negative f of x and rewrite it as just an x. So I call this just a drop it. So if it's even, then we drop it. So this negative is going to go away. It essentially flips to a plus. So the problem just becomes negative cosine of 3 theta. On our next one, again, we drop it because it's even, so this just becomes a secant of pi over 6. The remaining problems here, all of our other trig functions are going to be odd. So we've got odd on all of these. I call these a pop it, okay? So we've got drop it and pop it. So if it is odd, then we're going to pop it. The negative that we see on the inside will pop to the outside of the function. So we have our negative here, so we can pop it, and it's going to become a negative sine of 2 theta. We're going to pop it. We're going to get a negative cosecant of 135. And this one is a nice convenient one to check. If you evaluate the cosecant of a negative 135 versus a negative of the cosecant of 135, you'll in fact see that you get the same answer both times. On our tangent, we're going to pop it as well, but notice on this one, we're going to end up with a negative times a negative. So this is going to give us a tangent of 4 theta. And on our cotangent, we're going to pop it as well. So negative cotangent of 3 theta. Now, the next thing that we're going to look at are the periodic properties and how that idea, that fact that our functions will go on forever and ever in both directions, and how often that they repeat, that's the periodic nature, is how often they repeat, how that can be useful for us. So if we look, for example, here at cosine, we know that cosine is going to repeat itself every 2 pi, okay? So every 2 pi, we're going to get the exact same values for cosine. So when we look at this, I've got a cosine here, and then if I have a cosine and I have an angle plus 2 pi, if we recall, this is essentially a coterminal angle. So this is no different than just saying theta. And this theta plus 4 pi, well, this is, again, just a coterminal angle now with 2 spins. So this is also the same as a theta. So we can easily evaluate this by just recognizing this is a 0.2 plus 0.2 plus 0.2. Don't even need a calculator. We're just going to get a 0.6 for our answer. Sine is also will repeat every pi. So or 2 pi. So this also has a periodic nature of 2 pi. Now, what that means here is that if we're only adding a pi, that means that we're going to get opposite signs. So we can take this back and think about our all students take calculus, okay? If I have some angle, let's say here, and I add pi to it, then the next angle I'm going to get is going to be down here in tangent. It will have the same reference angle, but now it's going to be an opposite sign. Sign being positive, negative, not sine of our trig function. The same thing could happen here. If I have an angle here and I add pi, it's now going to land down here in cosine, so it will become negative. So when I look at this right here, what I'm thinking about having is actually my sine theta, my original sine theta, but if I add just pi to it, that's actually going to give me a negative sine of the theta that I started with. So that means that I'm going to have a 0.2 plus a negative 0.2, so this one would become 0. Now, cotangent has a periodic property of pi, and you've got to just keep these straight. You've got to know what those periodic properties are. So cotangent is going to repeat every pi. So now we're back to the same idea that we had here for cosine. A theta minus a pi is essentially going to give us a coterminal angle for cotangent. So this can be rethought of just as that original theta. Same thing with 2 pi. Now this is directly from our coterminal angles before, so this is going to give us a theta. Now, it's not saying that adding pi gives you a coterminal angle for theta or for cotangent. It's this idea here. If I'm here for cotangent and I add pi, I'm back to another place where I get the same sign, positive versus negative, for cotangent. So this problem is really a -2 plus a -2 plus a -2 or a -6. The next thing that we're going to look at are these Pythagorean identities, and you do need to know these, okay? Now, the first one is really, really easy, and truthfully, that's the only one that you need to know because the remaining ones are super easy to find based on this original sine, cosine, tangent, okay? Now, we can understand this sine squared, cosine squared equals 1. If we think about, let's say, this unit circle here, okay, we're going to consider this over here to be a unit circle. And if this then is a 1, I have a nice radius of a 1, we already know from before that to get to this point on the unit circle, this distance right here is considered, that x value is going to be considered my cosine, okay? And then this y value here is going to be my sine. And of course, if you did a Pythagorean theorem on this triangle, you would have sine squared plus cosine squared equals 1 squared, and that's just 1. So that takes care of our first one. Now, if we take this entire original first Pythagorean identity and we divide everything by cosine squared, so I'm going to divide by cosine squared x, I'm going to divide by cosine squared x, I'm going to divide by cosine squared x. If I do that and then clean this up, I know that sine over cosine is going to give me my tangent. So this is going to give me my tangent squared. And then cosine squared over cosine squared is 1. And then 1 over cosine squared is secant squared. So this is our second Pythagorean identity, okay? So we've got our first one and we've got our second one. Now, we can actually find this other one graphically. This is a little weird for some people to see, but I'm just going to show it here, okay? I'm going to call this piece right here, because I can see that it is tangent to the circle, I'm going to call this tangent x. And then, of course, this whole length here, actually going all the way, now I'm going to fix this so that you can see that the cosine was only from here to here. So if I go from my center all the way out, that is also a radius of my circle. And then this segment here, if I continued it, it would pass all the way through the circle twice. So I'm going to call that a secant. I'm going to call that secant x. And again, if you did Pythagorean theorem on this now bigger triangle, this one that's all the way here, you would have tangent squared plus 1 squared equals secant squared, and that is our second Pythagorean identity. The last one that we're going to look at is instead now we're going to divide everything through by sine squared. So I'm going to divide by sine squared, I'm going to divide by sine squared, and I'm going to divide by sine squared. If I do that, the first one's going to become a 1. Cosine over sine is going to be cotangent squared, and 1 over sine squared is going to be cosecant squared. Oops, forgot my second c there, sorry. There, cosecant squared x. And this is our third. So the only one that you really have to know is this first one that's really easy, and the remaining two are easily derived by just doing that simple division. The last thing that we're going to do is we're going to look at complementary co-functions, okay? And I'm going to have some practice for you guys. So I'm just going to jump to the end, and then we'll go back and see how this is actually working. Co-functions of complementary angles are going to be equal. So co-functions are just what they sound like. They are going to have this prefix of co on them. So sine and cosine are going to be co-functions. So what we're going to do is we're going to come over here to this triangle, and I'm going to start here at this angle of theta. And if I found the sine of this angle, I would say A over C because it's my opposite over my hypotenuse. Now, if I change my perspective on this and I move then to its complementary angle that's going to be up here, this angle up here is the angle 90 minus theta. Now, if I find the cosine of this angle, that would be the adjacent over the hypotenuse, and notice again that that is, in fact, A over C. If I look to the next one, I'm going to look at secant now. So secant and cosecant are co-functions because one has the prefix, one does not. So if I come down here to theta and I find the secant, that's going to be the hypotenuse over the adjacent, so that's going to be C over B. And then I go to its complement up here at 90, and I say, what is the cosecant? That's going to be the hypotenuse over the opposite, and that's C over B again. And the last one that we're going to look at is going to be tangent and cotangent. These are co-functions. So the tangent, opposite over adjacent, A over B. And if I come up here to its complement, and I'm going to say adjacent over the opposite, and that gets me an A over B again. Now, here's how this is useful, and there's going to be some practice. That means that the sine of 30 degrees is going to equal the cosine of 60 degrees because these angles are complementary and these functions are co-functions. The the secant, I meant to say there, the secant of, let's say, 20 degrees is going to equal the cosecant of 70 degrees because these are complementary, these are co-functions. The last one I can look at is I could say the tangent of, let's say, 10 degrees is going to equal the cotangent of 80 degrees because these are complementary and these are co-functions. So that's how we're going to apply this idea.